We now look at how to prove the extra theorem that we added to the events of increments. Again, this extra theorem asserts that V is still in the range of f from the interval of r plus 1 up to q. If we look at a visual summary, we'll see that currently f of r is less than v, and as a consequence, in the updates of the event increments, we actually increment the value of p from p into r plus 1. So now we are trying to assert that the element that we are trying to find must exist in the range, in the interval range of r plus 1 here up to q. So this is something we want to prove, and let's go back to Rodin and see how we prove it. And as before, we want to use two things and add them as a hypothesis. First, we want to make sure to use the sorting property, use the fact that the array is sorted. And the second, we want to make sure, we want to use the fact that the elements must exist in the array. Let's go to the proving perspective. And now this is what we want to prove. And this is the guard of the events. R less than Q is the theorem that we previously proved. Let's add the two hypotheses that we need. One, the sorting property of the array F. Second, the fact that V is in the range of P up to Q interval in array F. Let's add these two hypotheses. Now, we have to first expand the fact that V is in the range of P up to Q indices in array F. So let's expand this membership. If we remove that, and now we see because there exist some elements X such that X maps to V is in F. So this is what we get from the set membership as before, this expression here. So we have this, and now it has been rewritten as this expression here. And you're supposed to figure out why these two expressions are equivalents. They are quite obvious. Let's go on. So now we will also expand the membership over here. The only difference from this and that is previously it's from P up to Q, and now it's from R plus 1 up to Q. Let's expand this. Okay, so now we have an existential quantification, and because we have this instantiation already, so we will instantiate X to the same X as in the hypothesis. So we'll do that. So now we want to prove that X is in the range of R plus 1 up to Q. In other words, we want to prove that X is greater than R. And let's have a look at the hypothesis here. Because from this expression here, X maps to V is in F. That means f of X is equal to V. And we substitute this V here by f of X. So we have f of R less than f of X. And we look at here, we actually have less than or equal to relation here. And this does give us the motivation to apply modus tollens as before. So because we want to eventually prove X is greater than R, so that means we want to negate this less than or equal to relation here to greater than. So now let's so eventually we want to prove that X is greater than R. So we instantiate I as X and J as R. And let's instantiate that. And now we're going to apply the modus tollens rule. And remember that this we have to first prove the negation of the consequence, which will be f of X larger than f of R. And then once we have completed the proof, we will use the negation of the antecedents, which will include the negation of x less than or equal to r, which is x greater than r, and this will entail trivially the goal of over here. Okay, that's basically the guideline for the proof. So let's apply now the modus tollens rule, and we do that, and now this is the negation of the consequence that we have to prove. Okay, so this here we have v equal to f of x, and this indeed here is equivalent to f of x larger than f of r. It's just a different way to formulate that, and let's see if this will blow away by Rodin. It doesn't, so we suspect we may have to add something more about the typing for variable f to say it's actually a function. So to do this, we will use the search hypothesis function, and we have to say now f is actually a function from number to number. So we add that hypothesis, and let's try again if that will blow away. Okay, now it does. So let's go to the last sub-theorem that we have to prove, and here we can see that we are using the negation of the antecedents to prove the eventual goal. Okay, so now we have the pattern of not P or Q, and which can be rewritten as P implies Q. So let's do that. So disjunction to implication. So first of all, let's do it again because we have another occurrence of the not P or Q pattern. So let's do disjunction to implication. So now, so here we have implication, and we also have implication, and we are sure that the antecedent is correct. So we can trivially prove the antecedents by using the modus ponens. And the modus ponens says once we have proved that the antecedent is correct, then we can apply the consequence directly in order to prove the goal. So let's apply the modus ponens here, and the antecedents here is just trivial. It's just trivial because that's simply the typing information for x. So this will just blow away. So now we apply the modus ponens again to prove the to get the consequence by first proving the antecedents. So now R is in the range of 1 up to n, which is also trivial because R is declared to be from 1 up to n. So this will just blow away. So now let's have a look at what remains to be done. So we have x greater than r here, and all the others are simply just not relevant. So let's get rid of that. Oh, actually, we also certainly need the hypothesis that x is in the range of p up to q. We certainly need that for the upper bounds for x. So make sure you don't delete that. Okay, from these two, now it will just blow away. Yes. Okay, so now we have proved the second theorem that we have added to the events increments, and as you can see now, all the theorems related to the event increment have been discharged. And in the next video, we'll show you how the last theorem associated with the event decrements can be discharged in a similar fashion.